This is problem number 11.60, or sorry, 10.60 from chapter 10, obviously, and it deals with a special case of potential energy. So we have a spring, right, that is launching an object, but it's not described by a spring constant. The force, if it's Hooke's law, it'd be typically like minus kx, right? Where k is a spring constant and x is obviously the displacement, but the force with which they talk about it is cubic. So it's minus qx cubed. So what are the units? Part A, well, we got units, newtons on the left, and it would be, well, we got meters cubed on the right. And so that has to be newtons per meter to the fourth, just so we're all on the same page with the units. Part B is find an expression for potential energy of the sprung. I think they call it a sprung. So the potential energy as a function of x is defined as minus the integral of the force over that specific displacement from some initial value to some reference point rather to the location of interest. That technically would need a dummy variable. I mean, you're basically integrating x cubed, which is really easy. And so even if you don't completely understand the minus signs and the reference point of the potential energy, you can quickly get that this is just 1/4. Write that nicer, 1/4 qx to the fourth. So this is our potential energy for this specific spring. Again, most very stiff, if springs are really stiff, then this is actually a better model than the 1/2 kx squared. So for part C, then you have some data that you're given. You got a spring-loaded toy gun launches a certain bullet. But basically the energy equation is the only thing to use. So use initial kinetic plus initial potential equals final kinetic plus final potential. Right? That's all you do in that problem. But the thing is that the potential is not 1/2 kx squared. It is 1/2, so mv initial squared plus 1/4 qx to the fourth x initial equals, in general, 1/2 mv final squared plus 1/2 qx final to the fourth power, not squared. And so I think in this case, it's launched from rest and then it reaches 0. And so you basically have that 1/2, you basically have that 1/2 mv squared equals 1, no, let me be more precise about this. 1/2 mv final squared equals 1/4 qx initial squared. And so you can express, x to the fourth, that's the critical part. And so you can express this, that the launch velocity should be, let's see, canceling, well, no, you don't cancel the 2's, it's a 1/2 at the bottom. Square root of, so it's x initial squared times square root of q 2q over m. If you solve it algebraically. If I did that algebra right, looks like I like to think that I did. So that is the, sorry, a brief interruption. Let me just double check. So yeah, because we're solving for, oh, no, here, okay. Let me just get that right. If we're solving for V, we're going to get the M at the top and the 2's at the bottom. Oh, the 2 is at the bottom. So it's Q over, yeah, it's Q over 2M. Square, the 2 is in the wrong spot. 2Q over M. But then the radical closes and you got x initial squared. So I was off by a factor 2 the first part. I apologize. So that is the expression of the launch speed of the toy gun. You enter it in for your specific values for your particular problem.